Hi, I'm Lintian from UNC Chapel Hill. I'm presenting our recent work, GradICON, Approximate Diffeomorphisms via gradient inverse consistency. In this work, we propose an implicit regularizer used for training a medical image registration neural network. Medical image registration aims at finding physically plausible spatial transformation between two images. As we see here, the solution transformation should be able to warp image A so that warped image A looks similar to image B. In the figure, we can see some foldings during solving the solution, but the final transformation map is smooth and contains no foldings. The proposed gradient inverse consistent as an implicit regularizer to train a registration neural network. We call it implicit regularizer because it does not directly penalize on the transformation itself, like what the bending energy and diffusion regularizer do. Instead, it penalizes on the gradient of the residual error of inverse consistency. We demonstrate in the experiments that with gradient inverse consistent as an implicit transformation regularizer, it results in spatially regular maps and better registration accuracy on 3 practical medical image registration tasks. Before we jump into the introduction of methods, we first introduce the background of the problem. For a registration neural network, it aims to predict the transformation between two given images IA and IB. We train such a neural network via minimizing a similarity measure loss and a regularizer loss, computed over the training dataset. A simple and straightforward non-rigid transformation model for the neural network to predict its displacement vector field. It maps the corresponding pixels via displacement between their positions. To advocate physically plausible deformation with such a transformation model, one generally adopts the bending energy or diffusion regularizer when training the network. However, the issue with these regularizers is that because one directly penalizes on the displacement vector field, it limits the capability of the DVF to represent large and complex deformation. In terms of implicit regularizer, previously ICON proposed and proved that inverse consistency on the map yields regularized transformation map, but it has difficulty reducing percentage of foldings to 0, especially when the resolution gets greater. Here we propose to penalize on the Jacobian of the inverse consistency, and we demonstrate that in theory it is an implicit H1 type regularization when used to train a registration neural network. In addition, we empirically observe that it converges faster and is less sensitive to varying lambdas. Thus, we can learn registration network with the same architecture, same learning rate, and same lambda across registration tasks. Gradient inverse consistency can work with any structures of neural networks. In this work, we use a multi-step and a multi-resolution network structure that is trained with symmetric similarity measures and the gradient inverse consistency loss we proposed. We conduct experiments to compare gradient inverse consistency with other regularizers and show its convergence comparing to ICON. In addition, we applied GradICON on 3 different registration tasks. When comparing to other regularizers, we train neural networks with different lambdas and plot this dissimilarity and percentage of foldings in this figure. The experiments are conducted on 2 datasets. One would want a good registration model to have low dissimilarity and a low percentage of foldings. Thus, a good regularizer should not trade off too much between similarity and regularity, and it should be close to the bottom left in this figure. We can see in this figure that for the 2 datasets we test, gradient inverse consistency performs the best among all the comparing regularizers in terms of the trade-off between similarity and regularity. Next, we conduct an experiment to compare the convergence speed of GradICON and ICON. We select the lambda to keep ICON and GradICON producing the same amount of foldings. Under such constraint, we see that GradICON, which is shown as pink here, converges faster than ICON, that is green in this figure. From practical point of view, we test the GradICON on 3 medical image registration datasets that represent inter-patient registration and intra-patient registration. GradICON achieves best performance on knee and lung registration and on par with the SOTA method on brain registration. Moreover, because GradICON uses implicit regularizer that does not limit large and complex deformations, it does not need affine pre-alignment. Also, GradICON creates very small portion of foldings across all the 3 tasks. Lastly, GradICON is trained with the same network structure, same lambda, and same learning rate for all 3 tasks. In summary, we developed gradient inverse consistency that relies on penalizing the Jacobian of the inverse consistency constraint. It advocates well-regularized transformation maps. In addition, we demonstrate SOTA performance of models trained with gradient inverse consistency on 3 large medical datasets with a unified training protocol. Thanks for your attention. I will be at the poster session for any questions regarding our work. See you then.